keynote presentation of the event. Is the paper titled A Framework for a Comprehensive Mobile Data Acquisition Setting for the Assessment of Urban Heat Island Phenomenon. The authors are Mónica Peña, Faridadin Bagdatikaki, Joao Santos, and Andre Dori. So Mónica is coming to be the presenter. So the way this is gonna work is we're gonna have a 20-minute presentation plus 10 minutes Q&A, okay? For both people here in person and people on Zoom. So Mónica, all yours.
Good morning, everyone. Muy buenos días a todos. We'd like to start by thanking the organizing local committee for hosting the conference this year. This presentation, of course, will be in English. Let me start by introducing myself. I am Mónica Peña. I'm Colombian, and this is my hometown, which makes it very special for me to be here with you today. It's a great honor. And this presentation will talk about the work that we have been doing during the past 4 years, during the past 4 years. This is the project that I've been working on for my PhD. So the title of this talk is we're going to talk about urban heat islands, and we're going to talk about how are we understanding these islands in the context of data-driven modeling. So let's just get started. If I start speaking too fast, just raise your hand and let me know. I do tend to speak fast sometimes. So I can imagine that you all have heard about the heat events that happened in the last couple of weeks in Europe, particularly in Portugal, where the government has a call for a state of emergency. Also, perhaps you remember the heat wave of 2013, that this heat event killed about 15,000 people in France. Over the course of 4 months, the death toll exceeded 70,000 deaths in Central Europe and Western Europe. What happens is that these heat events, we feel them more in the cities. And this is because of something called the urban heat island effect. And this is what we'll be talking about today. So let me tell you a little bit more about what the heat island is. Basically, the materials that we use in construction, so asphalt, concrete, or bricks, these materials will capture the solar radiation, keep it, and bounce it back in the form of heat. This heat will stay in the cities and will create this increase of temperatures. So basically, during the day, these dark surfaces will collect heat, and during the night, you will release it, increasing the temperatures. The urban heat island phenomenon is defined as the variation in temperatures, the difference in temperature between the rural area and the inner center of the city. But this is not new. We have known about the urban heat island effect since the early 19th century. Researchers worldwide have model and try to understand this phenomenon, giving us a better understanding of what is happening in the cities. What is happening in the cities. Yeah. So basically, the predominant approach to deal with heat islands has been physics-based modeling. With this, what we try to do is to mimic the thermodynamic heat exchange processes within the urban fabric and the urban geometries. So basically, for these, we need very detailed information about the urban geometries and the materials that we use. This really is a very complex process. not only in terms of the physics behind it, but also in terms of the computation time that we need, as well as the, so the compute is quite expensive in terms of computation, it's very complicated and it's time consuming. It's just three main core problems that the modeling has. What happens when we take these modeling approaches, when we try to explain based on physics these urban phenomena, is that the phenomena itself is not taken into consideration when we're trying to plan our cities. When we build our cities, when we make these decisions that we all feel in the cities at the street level, these very complex simulations are causing that the urban heat island phenomenon is not taking part into this decision process. So you might wonder, and we also started wondering, how can we bring the urban design, the urban heat island, to the urban planning table so that we can take it into consideration when we make these decisions. To make matters worse, to make it a bit more complicated, we have two ways to measure the urban heat island effect in the cities. One is with air measurements, so canopy measurements. These are the air temperatures. Usually, these air measurements are taken via weather stations that are at fixed locations, normally outside the city. This, we do it to avoid interference with the urban elements. We also have surface temperature measurements. These surface measurements are normally taken via remote sensing technologies. The problem with this is that the remote sensing technologies will only take an image per month or two, and although they give us a whole picture of the thermal performances of the cities, we don't have this information as frequent as we need it. On the other hand, with air measurements, we do have this frequency, but we don't have the resolution that we need in the cities to understand what's happening in terms of temperatures. These two measurements are correlated, but as we are going to see later on during the presentation, they are not exactly the same. So the drivers of one might not be the same as the other one, and if we aim to mitigate one, we might cause negative effects on the other one and vice versa. So, to summarize, the core challenges that we have for the practicability of the urban heat island modeling, I will summarize that in 5 main points. So the first one is the accessibility and the usability for urban planners. So it's quite complex, and urban planners and decision makers don't really take it into consideration. We know that exists, we know that it's important, and in terms of heat events and what's happening now in Europe, for example, we know that we have to take it into consideration, but it's not part of the decision-making process because it's too complex. The data collection and the data resolution, the granularity of the data, what we need to make these decisions, is also not given as we need it. And this point is actually something that I faced during my PhD, the structure of the data. So governments store and collect their own data. Within their own country, municipalities store and collect their own data, and they do it in their own specific ways. The problem here is that we have the data, but the data doesn't communicate. There are different formats, there are different standards. So the structure of the public data is not always the same. An ontological approach here is quite needed. And as I was mentioning a little before, we have different urban elements, and these urban elements have an effect on the urban heat island, have an effect on how the temperatures change in the city. The link between these urban elements and the variation in temperatures in the city is not completely clear. This is something that we need to look into. And of course, when we try to mitigate these urban phenomena, we do it with one whole recipe. So we say, okay, these are the mitigation strategies. You, city planner, go and good luck with your mitigation strategies. And we give these prescriptions to all cities all over the world. But as we know, cities are not all the same. Cities may vary within the same city, for example. So what we need is a context-specific solution. We need to look at the cities and we need to look at the streets specifically within the same cities. So now we ask ourselves, I can imagine that you might also be asking yourself, how can we develop an easy to use model that can represent this complex interplay between these urban elements and these different levels of urban heat islands? But these different, when I say different levels, I mean air temperatures that we saw are taken by weather stations outside the city, and surface temperatures, and the difference in between the two. So how can we create a model that will explain this interplay in between these different levels of heat islands and the urban parameters, using data that is already available and that the urban planners can easily access? So this question brings me to three main objectives. Three main objectives of my research. That's me, and that's my bicycle. So we want to develop a user-friendly data collection pipeline that will take into consideration the data that is already there. Of course, we want to use the data, but we also may need some data that is not already there and is not available. How can we generate this insight that we need for this interplay between the urban morphological factors and the socio-economical factors at a micro level? When we talk in an urban context, the micro level refers to where the urban planners have an impact, so where they make the decisions, and this is at the street level. And we want to develop an easy to use urban planning toolkit so that we can encourage urban planners and decision makers, as governments and cities, to design and build their cities, taking the urban heat island into consideration. So urban heat island conscious planning. The research methodology that we follow was quite straightforward, 5 main steps. Many of you might be familiar with these processes. We start with the data collection. This data, as I mentioned earlier, comes in different formats, in different resolutions. So we need to process this data, bring it to the same resolution, integrate it in one whole data frame. So for example, if I will explain you later, I will tell you later how we do this. So we integrate it, and with this whole data set, we develop these models that will allow us to understand this interplay between urban features and the variations of temperatures in the city, which is the last step, the analysis and the toolkit. So this is when it becomes really, really nice. So we start with the data collection. And the first thing with the data collection is to know what we have, what data is available, and in which format, and how can we process this data. So for example, governments always have cadastral data sets. So building footprints, greenery, water presence, population, land use. This data we have, and we can already start processing it. What we don't have is the temperature data. So we don't have the temperature of the roads, for example, the surface temperatures, and we don't have the temperatures of air at the same spatial-temporal resolution. We also don't have the temperatures of the buildings, the facades, and the urban elements around our cities. This we don't have. I think I didn't mention, but I'm doing my PhD at the Netherlands, at University of Twente. This is relevant now because if you think of the Netherlands, the first thing that you picture is a bicycle, right? So when we thought about how we're going to collect our data, so we took a Dutch approach. So this is my bicycle. And then using the technology that we already had in our research group, we took my bicycle and we put different sensors that will allow us to map these temperatures. So for example, this one is a thermologger. That thermologger will record the temperatures of air and the temperatures of the road as I was cycling. We have a thermal camera. This thermal camera was taking thermal images of the buildings as I was cycling. We have a GPS antenna. This is important because we need to keep track of the specific points where I was cycling and the temperatures at that point, the 3 temperatures that I was capturing. And of course, if I'm cycling, then I do want to know that I'm recording the data properly. So we have a display. Then I was just constantly checking if the data was being recorded. Okay. We ran a case study in the middle of Apeldoorn. This is a mid-sized city. In the middle of the Netherlands. The city name is Apeldoorn. It's a mid-sized city, about 150,000 people, oceanic climate conditions. And we designed a route, 8 kilometers route. And the goal of this circuit was to capture different urban morphologies, different geometries, different type of buildings, different types of vegetation, land use, if it was in the district center or if it was in the residential center. And we also wanted to capture the difference along the day. So the temperatures in the morning, the temperatures in the afternoon, and the temperatures in the evening. Not only that, but we also wanted to see the variation in temperatures all along the year. So I was quite happy thinking that I was gonna get really fit because I did this 3 times per day. It took me 1 hour, so 3 hours per day. I did this 2 days a week over a whole year. Spoiler alert, I didn't get any fit. So I collected all the data and now I had to integrate it, right? So as I mentioned earlier, the data comes in different formats. It has at different resolutions. What we did was we took a street. So from intersection to intersection, that's how we define the street. And within that street, I created a buffer, a 15-meter buffer around the center line of the road. And I brought down all the urban morphology indicators, for example, the average height of the building within that buffer, or the population within that buffer, or for example, the greenery density within that buffer. So I will have one street and all these different socioeconomical and urban morphological indicators. On top of that, I also calculated per street the average temperatures of surface and air. And of course, the buildings. We ran in total 36 data-driven models, machine learning models. We use 12 different configurations of the data that I collected. So for example, morning, so it was the temperatures that I collected during the morning, the afternoon, the evening, and the whole day. So in total, 12 different configurations of the data set, 36 deep models. We use a neural network, random forest, and decision tree. At the end, what we saw is that the random forest performed better in terms of prediction. So for example, if we look at the data for the whole day, the air measurements, the random forest performed with a mean absolute error of 0.24 degrees, which is quite low. For the surface, it was a little higher, 0.87. This is our degrees Celsius. So it is quite low, but it is still, these are temperatures than I collected. And the temporal differential was the difference between the surface temperatures and the air temperatures. So the variation within that resolution. And here is when we get the data to talk. So we wanted to see what was happening in the cities, right? So we wanted to see how the urban morphological factors and the socioeconomic factors were affecting the temperatures in the city. And this is really nice to me because then the heat islands are already saying, okay, these are the parameters that are having an impact in my temperature. And I always say, like, now my data is talking. And what we see here is that the morning, afternoon, and evening temperatures for the air measurements will have a different dynamic all along the day. So the features that are important in the morning are not the same that are in the afternoon, and they are not the same that are in the evening. And this to me was already quite exciting. And if we go a little further, we see that it happens also when we look at canopy airs, so air measurements, surface measurements, and the temperature differential. But what we see here is that at all levels of urban heat island within the reach of the urban planning, the urban planners, the features may have different impacts. So the mechanisms that create these heat islands are different if we evaluate surface, air, and the differential, which is what I told you a little earlier. On top of that, we develop a quite easy to read toolkit based on a decision tree. So the performance of the decision tree wasn't as high as the random forest. But here the decision tree allows to read what the algorithm was doing. So we could see how the decisions were being made. And because of that, we could create these thresholds. So for example, I have 5 categories of urban heat island potential in the city. And these again are at the street level. So if I have a specific street with this configuration, so for example, the first heat island, the green one. So if I have a predominant land use within that buffer, or as parks and conservation, within that building density, vegetation density, population and traffic count, then I will know that the heat island potential in that specific street will be low, and so on with this 5 categories. And this is quite easy for the decision makers to just read. It gives you already an insight of what is happening. And that's what one of the goals that I had, to provide this information so that they could take it into consideration when they're making their own decisions. So I would like to conclude my presentation with the lessons that I learned during these 4 years, and especially with my bicycle, and where we're gonna be and what are we doing now. So we need to know what data, and we need to know how to collect it. This is very nice because it opens the question of, can we crowdsource the data? Can we build these bicycles and we can send them around, and can we collect this data that will allow us to design our cities better? I imagine that when I say an ontological approach, many of you might be like, yes, we want an IFC for the data that we're using at an urban level. This is something that is missing in the cities, in the governments. And when we develop pipelines and models for one specific city, we want to use the same pipeline in another city. We want to be able to communicate these 2 similar cities with similar wishes, but with different drivers of the temperatures. But right now, the structure is, the data is structured in different ways, and it does not allow us to do this. So an ontological approach is needed when we talk about urban phenomena. As I mentioned earlier, normally we evaluate air temperatures or we evaluate surface temperatures. They are both correlated, but as we saw earlier, they are not exactly the same. They don't really behave the same. So we need to evaluate them both at the same time and both at the same spatio-temporal resolution. One size fits all approach doesn't work. It does not work when we talk about urban planning. It does not work in many other different contexts, but in this particular case, we need to look at the specific situations within the city, outside the city, and within the country. So we need to design these models that allow us to explain, to give voice to the cities, so that the cities and the morphological and socioeconomical factors can tell us how they are affecting the temperatures in the cities. And this is something that we are working on right now, is when we talk about data-driven modeling approaches, we always ask ourselves, how generalizable are these models? Can I develop a model for one city and use it in another city? We try this. The model that I developed for Apeldoorn, I tried to use it in Montreal, Canada, and the model for Canada, for Montreal, I tried to use it in Apeldoorn. Spoiler alert, it's not generalizable. It might be because the cities are quite different, not only in location, but in infrastructure. But then it does raise the question of how generalizable are the models? Can I take the model for the middle of the Netherlands and use it in a city nearby? Or how far can I go? Or can I use the model that I developed for Montreal and use it here in Bogota, for example? This is something that we're working on at the moment. And Second to last, when we talk about applicability, when we want to bring our research to practice, what we learn in our project, we want to bring it to the people, right? So when we want to do this, the simpler the models, the more explicable they are, the better. So we want to simplify everything that we're doing so that people can use it. So applicability translates simplicity. And finally, this is something that I have in my to-do list. We want to look at the relationship between temperatures in the city and building energy use. So how are we designing our buildings, and the temperatures of these buildings, how are affecting the temperatures within that street, for example, and the other way around, how the temperatures in the city are increasing the energy use of these buildings. And with this, I would like to close my presentation and open the floor for questions or comments, if you have any.
So any questions here in the auditorium or in Zoom? If you are in Zoom, you can raise your hand, and then our Zoom staff will allow you access to the microphone. So there is one question here in the auditorium.
This is Thomas Czerniawski from the University of Arizona State University. My question is about your bicycle. Is this a commercial product, or is this something that you developed?
No, it's something that we developed using the technology that we already had in our research lab. So
could you talk about how long the development process took and how many people were involved in developing the bicycle?
Me and my supervisor. No, so we had different sensors. And in our research group, we already measure temperatures within the asphalt process. When we build roads, we lay the asphalt and we measure the temperatures of that process. So that same technology I use to synchronize the sensors. So that was already quite handy. Putting the bicycle together took about a month or two. Deciding where to place the sensors. If I was cycling this way, if I wanted to capture the data from these buildings or from these buildings. But for me, what took the longest was to design the circuit, because I wanted to capture as many urban elements as possible. So I had to go around the city many times deciding what will work and what will not work. At the end, it was at risk because, of course, I was collecting data for so long, and then to come down and see like, oh no, I missed one street. Then it was a bit of that part. It was for me what took the longest.
There is another question here in the auditorium. Are there any questions in Zoom? No? Okay.
Mónica from the University of Illinois. Very interesting presentation. I had two questions, more clarifications. When you're using the thermal camera, when you were capturing your data, did it reach any equilibrium state? Because apparently when you were driving, or when you were biking around for 1 hour, you had difference in temperature too, right? And then depending on how temperature changes throughout the day, obviously the equilibrium makes an impact on it. Can you speak to that? That's my first comment. Second one is, it's interesting, your random forest outperformed your neural network. I'm guessing the size of the data is small. Of course, it's simple, it's faster to compute, but the size of the data is probably small that you had a better performance on random forest. Can you speak to the size of the data? I know it's been extensive already, but if you can speak a little bit more about numbers, that'd be great.
Yeah,
thanks.
Okay. For the first question, let me try to refresh to see if I understood correctly. So it's about if the thermal camera reached an equilibrium so that the temperatures that I was capturing weren't changing anymore. Is that correct? No, it did not happen. That's why it came to handy to have this display. I could see how one building will have 40 degrees. And of course, sometimes I have different urban elements. So if I had one building here at 40 degrees, I can have a car here or a tree, and the temperature will just immediately drop. So I was kind of constantly looking at that because I was afraid that at some point I was trying to cycle very slow, but of course I was cycling. And I didn't know at the beginning if the camera could keep up with that. But yeah, so the temperatures didn't reach an equilibrium point, not in the morning, afternoon, and evening, and not during the seasons. I did see that in winter, for example, the temperatures didn't change as much. So they were a little bit more stable, also on the road. And the second question, I was also quite surprised that the random forest performed better. I was expecting that the neural network will be better, but this is the same as one model doesn't really work with all problems. And this is something that we always talk in data-driven modeling. So what we expect of a neural network to do might not be the same with this specific data in an urban context. The size of the data sets, I don't remember exactly what it was, like 60,000 data instances at least, I think. So in my head, it's not small. It is quite a large data set. The random forest in terms of time did perform about the same that the neural network. So it wasn't that it was a lot faster, but the neural network did increase in complexity quite fast. So the hyperparameters of the neural network were going out of control when I was optimizing the hyperparameters to make it perform better. It is true that the difference in performance wasn't as big. So I could also use a neural network, but the complexity of the architecture of the network was increasing, and the random forest did show better performance, and it was also a little bit simpler and faster.
Thank you, Mónica. With this, this session concludes. Applause.